Electrification and decarbonization. We, in the hydronics industry, we say hydronics is the best solution to electrification. We also feel that hydronics is the best solution to decarbonization, and certainly it's the best solution to lower global warming potential. So those are pretty bold statements, and we'd like to show you how we can do that. So there's politically going on in the world attempts to limit fossil fuels, particularly for heating. These are some countries in Europe that have done some legislation, I guess we'll call it local ordinances, to limit the use of fossil fuels. There are some states, mostly on the east and west coast, that are doing the same thing. And these are cities in the east and west coast that are doing that. So again, this is here to stay. We can't ignore it. Okay. With that said, we need to approach this in a logical sequence and make some sense out of it. So as we electrify more and more things besides cars and buildings and whatever, it's obviously going to put a higher demand on the grid. And there have been several organizations, folks that have looked at this. Here's the Electric Power Research Institute said that electrical load could grow as much as 50% by 2050. American Society of Civil Engineers right now said the grade for the U.S. electrical grid is only a D+. Ooh, that's not good. And American Public Power Association said the grid must be updated. So we need to pay attention to how we're going to impact the grid with this electrification. That's really the bottom line. Okay? This was an estimate by the American Gas Association. On the left shows you the current demands, and you can see here that the peak is summer peak for air conditioning. And as we shift more and more towards electrification in our industry, you're going to have to convert heating systems to electricity. And as a result, the load's going to shift. And so we're going to have a winter peaking system rather than a summer, and it looks like you could almost double the electrical demand by adding electrical heating. Okay? So, I mean, that's the bad news, but it's also the good news. It's the opportunities. What can we do then to help out this situation? This is an interesting one. This was Toronto, right, Jay?
Yep.
Okay. They looked at electrifying all their existing systems. And they looked at it two ways. One was an air source heat pump, that's the dark blue, or you could do ground source, which is the light blue. And the one that you want to pay attention to is on the far right over here, okay? So if you use air source heat pumps, it's going to be twice the cost to basically develop a more robust generation and grid system as opposed to using ground source. So there's a pretty, I guess we'll call it, significant difference in how you're going to approach electric heating and the type of equipment that we're going to put in there. This is another interesting one. This is what's happening in Europe. This is conversion to renewables. I'm kind of familiar with that. Germany currently is about 30% renewable, and they're running around 30 cents a kilowatt hour for electricity. Our average cost in the U.S. is around 10 cents, and they feel when they get to where they're trying to get to, that price will double to 60 cents a kilowatt hour. So it's going to get more expensive. That's just the way it is. Higher demand, fixed supply. This is pretty simple economics, huh? Okay, so what we can say is, with electrical heating systems, the rates are going to rise just because we're going to have a higher demand. As we shift to renewables, the rates are going to rise. And so how are you going to reduce those demands? We think hydronic HVAC systems are the answer. Now, in particular, you want to use some kind of heat generation equipment that has a coefficient of performance in heating of more than 1, because COP equals 1 is straight electric resistance heat. So here are some available heating sources if we're going to do electric heating. At the top is just straight electric resistance, baseboard, boilers, etc. That COP is 1. Geothermal heat pumps, nice COPs, 4 to 5. On the right-hand side, it's important though, you need to look at the temperatures that AHRI rates those COPs at, okay? Notice that those temperatures are all fairly high when it comes to heating. I live in an area in Montana, the design heating temperature is minus 40 degrees Fahrenheit. It's also minus 40 degrees centigrade. And I haven't seen minus 40 at my house for at least 2 years. February of 2019, when I walked out of my deck, the thermometer said minus 40 degrees. So that's been an impact that you see over here, okay? All right. Let's talk about air source heat pumps, air to air in particular. These are mostly residential products. With an air source heat pump, as it gets colder outside, you have fewer BTUs available to extract from the air and move into your house. That green line on the right is a classic air-to-air heat pump that the industry's been manufacturing for many, many years. Notice how the heating production falls off with outside air temperature. There's just less BTUs. Okay. The orange line is the new variable speed inverters, sometimes referred to as VRF. What's interesting about that is the VRF folks claim they can produce the same BTUs independent of outside air temperature down to, what is it, about 10 degrees, something like that. Well, that's kind of interesting. How would you do that? That looks to me like a violation of the first law. Huh? Are we getting something for nothing? Well, it turns out that is true. Okay, that unit can produce the same BTUs at 10 degrees as it's producing at 40 degrees. So where did the heat come from? Anybody know?
Power you put in the compressor.
There you go, right. It's got to come from the compressor, right? So what they do, which is really pretty smart, is they speed up the compressor. We have a higher mass flow rate, right? And so we can get more heat transfer across that condenser coil, and we can produce more heat. But it's still the first law. You can't get something for nothing, correct? So how do I say this? With variable speed systems, compressors, if the efficiency goes up when I slow the compressor down, what's going to happen to the efficiency when I speed the compressor up? It's going to go down, right? Okay. So this is what it looks like. So the constant speed unit is on the left, and then your variable speed inverter is on the right. And what's interesting about that is if we go to 0 degrees, that old-fashioned constant speed guy is still producing a COP of about 2, whereas your new variable speed guy is 1. In other words, it's straight electric resistance heat. It does produce the heat, there's no question about it. But you're doing it with a COP of 1. It's like electric heat. Okay. Another interesting thing about air-to-air heat pumps, this is residentially, is that if you size the unit for cooling, which is typically what you do, it's a condenser, right? And we make it reversing as a heat pump. You basically run out of poop at about 15 to 20 degrees. So here's a graph that's showing you the ambient temperature here and the capacity going up. The two lines, the two blue lines, represent the heat loss, and the other lines represent the heating capacity of the unit. So you can see here on the left where they cross is around 15 degrees. So you just run out of poop. You can't eat. All right? So, I mean, air units are good in mild climates, but in really cold climates when it's minus 40 degrees, well, that's not going to do the job. Another problem with air-to-air guys is unfortunately, because we're extracting heat from the outside air, as it cools down, it's going to condense, and if it gets below freezing, that water vapor turns to ice. And now I have to thaw out the coils on the left here of that condensing unit and get rid of the ice. Anybody got an idea how you do that? How would Are you gonna melt it?
Electric heat.
Electric heat, yeah, right. Well, sort of. Rather than put in just an electric coil to melt it, what these guys do is they get the heat from the building. Right? So that unit goes into air conditioning mode. And I have a heat pump in my house, and I know all about this, and I live in a cold climate. So at 20 degrees, not only don't I have enough heat, but it's putting out 55-degree air on my back when I'm sitting at my table. That's very uncomfortable. So the air guys know all about that, and so they actually have installed an outside air thermostat that shuts this thing off at some temperature, outside air, so that you're not uncomfortable and you get enough heat. And I started out with mine because I wanted to get, as much efficiency I could, and I started at 10 degrees, and I can tell you right now it's set at 25. Because my body just can't stand 55-degree air blowing on it at 20 degrees outside, and it's snowing, and I'm thinking I should be warm, but I'm not. So I just shut this thing off at 25 degrees, and I go to my backup heat, which is the propane furnace. Then I'm comfortable. We're all happy guys, right? Okay. So again, there's some limitations to these particular devices. All right, now let's look at an air-to-water heat pump. So instead of an air-to-air, this is air-to-water, and we like water and hydronics. Okay. So this is the operating envelope for a typical air-to-water unit. And there's a couple things that you'll notice. There's a blue line there that says 100-degree lift. So in today's world with the refrigerants we're using, the maximum lift from the heat sink to the discharge temperature of that air-to-water unit is roughly 100 degrees. Okay? And you can see here, this is a typical manufacturer's operating envelope, and there's the 100-degree line, and so it's about 100-degree lift. The other thing is that at cold temperatures, this guy is a compressor, and it's got to have lubrication so it doesn't burn up. And when it gets cold, the oil starts to not flow as much, the viscosity is going to get higher, right? So the manufacturers have just said, look, let's just turn the thing off, let's protect it, we're not going to have any problems with it, and so it just flat shuts off at about 5 degrees. Okay? So if you're in a cold climate, it's not going to provide 100% for you when it's really cold. Okay. Here's a water-to-water heat pump. Notice we've been going from air-to-air to air-to-water. Here's water-to-water. Whoa, I like that. Huh? Look at the lift here. At the left, 41 degrees, the lift says 158. So wow, that's almost, 120 degrees? Yeah, you're getting a higher lift. And I'm getting nice warm temperatures off of it. 158 degrees. Ooh. I can heat my house, I can heat my hot water. This is great, right? We just need to find a source that's on the left there, 40 degrees. So where would we find a source at 40 degrees for a water-to-water? Huh? Anybody know?
In the ground.
In the ground, yeah. And so I created this graph, and I call it demand factor on the left. So this is the demand on the electrical grid from using electric heating from these different kinds of heat pumps, okay? So it's really just 1 over the COP, so to speak, all right? So you start out here at the right-hand side, and we're going to say the demand factor is 1, okay? So whatever the demand is, we're just going to call that 1 at the start of the heating cycle, okay? As it gets colder outside, the air source heat pumps, those are the guys at the top, they're going to put more and more demand on the grid, and then, as an example, the air source, that's the green guy, we're just going to shut it off at 20 degrees because it's run out of poop and it's making me uncomfortable. The orange guy, which is the VRF, the variable speed guy, is starting to lose its efficiency because, again, we're speeding up the compressor, and at some point, then it's going to be full electric heat. The purple guy, that's the air-to-water unit, it's more efficient for a longer period of time, isn't it? Huh? Down to about 0 degrees, and it finally just says, I'm going to shut off. Meanwhile, the guy at the bottom, the blue line, that's the geothermal unit, is just happy as a clam. It could care less what's going on outside. It continues to put out plenty of heat, no extra demand on the grid, and that's a pretty slick way to do it. So now let's talk about how you would actually do this in the real world. Because the industry is starting to produce equipment that can do all this. Now it looks a little confusing here, so I'll just try to make this real simple. This is an air to water kind of heat pump. And one of the things that you want to be able to do to, again, reduce the demand, since it's water, right? And we got to heat domestic water, and we're throwing BTUs away in the summer, why don't we recover those BTUs and heat the domestic water? So what we want to do then is try to utilize, we'll call it net energy, and not throw any BTUs away when we could use them over here to heat something else, okay? So this is the air-to-water unit guy. So in the lower right-hand corner is an air-to-water heat pump. Notice there's two tanks up here, a red one and a blue one. So that air-to-water heat pump, in this particular case, it's not simultaneous heating and cooling, it's either or. So it just bounces back and forth to keep those two tanks full of hot and cold water, and now you got hot and cold water, and you can heat and cool your building. Great. Okay? Really simple. All right. One of the difficulties, again, is that lift. So if it's 0 degrees outside, or 5 degrees, and I only got a 100-degree lift, I'm going to get 105 degrees off the unit. That's not a high enough temperature to heat my building or my domestic water. So the industry is coming up with another guy. That's the water-to-water booster. So it can take water at, say, 100 degrees and boost it to 130 or 140, whatever you want. So that's pretty slick. So we can take this unit that wasn't really getting us quite what we needed and boost that up to get what we really need. Okay? That's what's going on there. So that on heating, you start at the lower right with the air-to-water unit, you flow to the left, the booster kicks it up, and now we got nice warm 130-degree water in the storage tank up above. If you live in a cold climate, you're going to need that red guy on the left there, that backup boiler. Because remember that air-to-water unit is going to shut off at 5 degrees and say, I've had it, we're done. So now you got to have some kind of backup. Could be electric, but what's the COP of that guy at minus 40 degrees? 1. You want to use gas, folks. Nothing wrong with using gas here. We're not saying it's 100% electric. We're just trying to say, look, we want to use less gas and we want to use more electricity, right? And if you're in that cold climate at minus 20 degrees, it's not going to run that much because the number of hours below that 5 degrees is not a big percentage of the total hours of heating. It's fairly small. We'll show you what that looks like. Now, we threw in another little wrinkle here, which is what are we going to do with those BTUs in the summer instead of throwing them away? So, if you take that chill water storage tank, in the summer we would normally take the heat and run it backwards through the air to water and throw the BTUs away. But here we're going to go straight left in the heat exchanger. See where it says heat recovery piping circuit? That's 55-degree water because we're cooling. Run that into the booster, add 100 degrees to it. Poof. We got now BTUs that we would have wasted. Now we're going to heat our domestic water. We challenge any air system to do that. Okay, so that's an air-to-water unit. If you look at the energy consumption and energy costs of that configuration, that's the guy on the left. That's air-to-water with the booster, and we'll call it net energy heat recovery. The second one from the left is a standard DX, and the next is a standard VRF, and the one on the far right is a standard gas boiler with electric chiller. So there's a huge increase in efficiency by being able to recover those BTUs. So here's a water-to-air heat pump. This is commercial stuff now. This is not residential. So this is a water-to-air heat pump. You see the water source heat pumps at the top. You have a condensing loop that's running around there, right? That's the purple guy. And to that, you would normally connect a boiler because that water-to-air heat pump cannot provide all the BTUs in heating. If I had a COP of 4, that means that 1/4 of the BTUs comes from the compressor, the other 3 has to come from the loop, which is the backup boiler. But if you want to do all electric, we're going to use an air-to-water heat pump instead of the boiler. All right? It is pretty slick. So we have cascading heat pumps here. You got an air-to-water providing the extra 3 BTUs for that COP of 4. Again, if you're in a cold climate, you're still going to need the backup boiler. Okay? On the right-hand side, you're going to see the cooling tower and another heat exchanger, because what we can do here is we can take that heat that we would normally throw away through the cooling tower and run it through another heat pump, another water to water, and heat the domestic water. Yeah, right. Ooh, I'm gonna throw in another wrinkle here. Not that I'm trying to confuse you, but. So, all this stuff here in the lower left, same here, costs money, right? And we're trying to do this and not impact your budget and your pocketbook. So we in the hydronic industry have come up with a way to do that with no increase in cost. It doesn't violate the first law. It's not something for nothing. So in the upper right-hand corner, you see the distribution system up there? That's normally a 4-pipe heating, cooling, 2-pipe heating, 2-pipe cooling. And you'd have another 2 pipes for domestic water, but there's only 2 pipes total. Whoa, how do we do that? We're going to cut the number of pipes that it takes to heat and cool your building with a 4-pipe fan coil, and we're only use 2 pipes. We're going to use single pipe technology and integrated piping, where we're going to do double duty with the domestic water to do heating and cooling. We're going to pump domestic water, hot and cold, through your fan coils to make you hot and cold. Huh? So we can take a 6-pipe system and make it 2. Over here, this is the water source heat pump. Here we're going to use fire protection piping. We're going to take the fire sprinkler system and run condenser water through it. Now you get a free piping system here as well. Anybody ever done any of these? Nobody. Okay. Well, I've done hundreds of them. Starting back way back in 1970. So we in the hydronics industry are doing some things. It doesn't appear sometimes that we are, but we really are. Okay, so there's a water-to-air heat pump. Now here's a water-to-water heat pump. Okay, same kind of thing. The difference is in the lower right-hand corner, that's the water-to-water unit, and it's going to get its heat or reject heat to the ground. Okay. That could be a well system, dedicated well system for that particular building, or we're now seeing community geothermal systems. They're being referred to as ATL, ambient temperature loops. It's just a piece of bare pipe laid in the ground, it's condenser water running around your neighborhood, and then everybody can either extract heat from that ambient temperature heat or put heat back into it through their own individual heat pump in their building. So that's pretty slick. And again, we're going to do heat recovery. So see here on the chill water tank on the right, we're going to do heat recovery. We just go straight left into another booster, take that 55-degree water, bring it up to 130 degrees, and we're now recovering all those BTUs instead of waste heat. We hope can help you is to give you some tools to evaluate these different systems and help discuss this with your customers. Okay? So our Hydronics Industry Alliance has created a tool we call the Building Efficiency System Tool, BEST, B-E-S-T for short. It's some software that helps you evaluate first costs, energy costs, maintenance costs of different kinds of systems out there. Okay? How many of you used Carrier Hack or Frame Trace or some of those kinds of programs? Okay. For those of you that have used them, they're comprehensive, but they're complicated and time-consuming. So our gentleman over here in the blue, I'm going to pick on you because he's sitting closest. So if you're going to take a typical building and evaluate, say, 4 different HVAC systems with whatever software you use, how long would it take you to do that?
It could be quite complicated. It could take a long time.
Okay, we're talking days, a week, what?
Probably a day.
A day at least, yeah, maybe longer, right? Mm-hmm. Now you got to get paid for it, right? That's more difficult than actually doing the analysis. It's getting paid for that, right? Okay. So how would you like to do that instead of 2 days and 2 hours? Would you like that? Okay. Well, that's what BEST can do. All right, let's see if I can get this computer to. I'll just do a quick demo here of the software. And by the way, this is available on our Hydronics Industry Alliance website. Type in Hydronics Industry Alliance in your search bar or in your search engine, and it'll come up, and you can get on our webpage, homepage, and download the software. The best part of it is free. I'm trying to make this easy for you. Okay. So one of the things about this software is we want to make it really easy to use. So it's quick and it's intuitive. This is the opening screen. We call this the simple wizard. You just have to tell us some basic information. And this is software that helps you at the beginning of a project where there's very little information on it, okay? And it helps you narrow down the choices that you may want to spend more time later on analyzing. You need to tell us where you're located so we can get the right weather data. We have weather data now for North America, about 1,000 different locations with hourly weather data. The other thing is we've simplified the building. We're going to model a building as a cube, length, width, and height. We don't care about the building. We only care about the HVAC system. So this is not software that you can evaluate different building configurations and orientations, okay? So let's say that this building is 300 feet, 100 feet, and let's say it's 6 stories high. Now, the other thing we've done to make this quicker is we have some typical buildings here, and we have pre-configured what we consider to be the most used kinds of HVAC systems in these typical buildings. So this is an apartment building. Down here at the bottom, the first one is an air-cooled fan coil, 2 is a split system, DX, 3 is a water source heat pump, and 4 is a DX, or is another DX VRF system. Upper left is the energy, projected energy cost of the 4 different systems. Looks like the 2 hydronics are more efficient than the 2 refrigerant systems. Upper right, life cycle cost. Looks like, again, the 2 hydronics are the winners. Upper or lower left is first cost. And so you can see here that the DX is lowest first cost. We would all expect that. But here in yellow is the projected paybacks. The 2 hydronic systems, fairly decent. You know, we're probably talking less than 5-year paybacks on both of them, which isn't bad. Okay, now we'll go to the advanced system wizard. So this is the project screen, and we just regurgitated the data that you gave us, locations, building dimensions. Now, if you're doing this, again, at the beginning of a building where you don't have a lot of information, you haven't done loads, we estimate a BTU per square foot load based on your location in a typical building. If you want to change that, you can change it to whatever, or if you've actually done your own load calculation, you can enter it here, okay? We're just trying to get you started. We've also defaulted the utility costs for each state based on what state you've chosen over here. This is data we derived from the Department of Energy, EIA, Energy Information Administration, so these are the average costs for these utilities in these states. Go back to the energy cost screen. There's what you saw before. Those are the 4 systems with the projected energy costs. Here's the life cycle cost of those 4 systems like you saw before, okay? So, if you don't like what we have selected for you, you can select it yourself. So here's the advanced system wizard. We have pre-configured different HVAC systems just by choosing from a drop-down menu the most common HVAC system. So let's do a fan coil, but instead of a air-cooled, we'll do a water-cooled, and let's do that. We saw up there, it's a 2-pipe integrated system. I choose an K. I go back to energy costs, and now you can see here that water-cooled fan coil is the most efficient system. Okay? That was pretty quick and easy to do. If you don't like that and you want to configure your own, go to the system screen for each one, and you can configure whatever system you want. Just from drop-down menu. On the left, heating and cooling. In the center, we have pipe and duct systems. And on the lower right are all the plumbing units. So if you want to go through and configure this yourself, you can certainly do all that. Now, just for grins, let's go back here. And we were looking at some interesting configurations. So here's a water-to-air, air-to-water heat pump system with heat recovery. We got an air-to-water heat pump, we got a booster, and we got a backup boiler. All right? Those are the primary heating sources. So if we go back to here, so I can do a heat pump, I can do an air-to-water. We default for you the backup boiler and the water-to-water booster. And we have something here called load split. So if you have different kinds of equipment, you can choose the load split between the different kinds of equipment. An example, maybe you had an older boiler replacing, or you were adding a new boiler, different efficiencies, and you can then change the load split between these two of them. So there we've just modeled that system that we have. Okay, let's look at another one. This is the water-to-air heat pump with heat recovery. You got a water-to-air heat pump, you got an air-to-water as the backup and a booster over here. So let's go back to here. I want to do for heat source number 1, water-to-air. So there's a water-to-air. We're going to do a water loop. I'm going to do a boiler. But I really want a first stage, so to speak. I want a air to water, and then if that doesn't work, then I go to the boiler. So there's a water to air with an air to water and a boiler. Multiple sources. I'm not aware of any of the other software out there that allows you to do this quickly and this easily. Okay, now back to, if we're doing these kinds of systems, again, if you're in an area that you need backup heat, it doesn't make a lot of sense to use electric resistance when it's 40 degrees outside, minus 40 degrees outside. The grid's not going to support it. We're working on a job right now in the Rocky Mountain area, and it's an air to water with the booster and the boiler, because that design temperature is minus 20. And if we'd have gone to an electric boiler resistance, you'd double the size of the electric service, which would have cost the owner about $250,000 extra for the electrical service. So we went to a gas boiler as the backup. So here's one that I've done real quick like. I've configured here, system 1 is the air to water with the gas boiler. System 2 is the same thing with an electric boiler. 3 is an electric boiler all by itself, and 4 is a straight gas boiler. The point here is, if you went to this system here, which is the air to water with booster, but electric boiler, the demand on the grid is the same as doing electric heat. If you went with a gas boiler here, look at the difference in demand. It's not much different than it would have been just for straight cooling, and I've reduced my gas consumption about 95%. Right? And here, just to look at this particular one, let's see here, the design temperature is right around 0 for this location. So bin data right here. These are the hours. So below 5 degrees, there's maybe 100 hours. So why put an electric boiler as a backup for only 100 hours of use? Go to the gas boiler. That's the whole point of doing it. So we've now created some additional tools for you to help you make these kinds of decisions.
When we're talking about air-to-air,
Yes, okay.
air-to-air heat pump,
Yes.
when that heat pump, okay, goes into defrost,
Mm-hmm.
sure, it goes into cooling, and the heat takes the heat from inside the building and defrosts the outside. Okay?
Mm-hmm.
But right now, there's something called the Cold Climate Heat Pump Challenge going on, and it's
Yes.
for Minnesota and like that, down to 25 degrees below zero. And in the specifications, it says that you have to turn the electric heat on when that unit switches to cool in the winter. The electric heat comes on 15, 20, 25 kilowatt electric heat.
Sure.
Okay, so that electric heat goes into the air, goes back into the machine, and goes outside and defrosts the outdoor unit. That's a lot of electric heat.
It's right there, Ralph.
There it is.
It's right there, right? You haven't reduced the demand on the grid. Yeah, it'll heat. I don't question that at all. Sure, right? But you've impacted the grid.
Oh, yeah.
We don't have a grid in the U.S. electrical grid that can support all this. But being smart about it and using different kinds of configurations, we can do this, even with the existing. Like I do at Ralph, I have an air heat pump. Like I said, 25 degrees, I just flat shut it off, and I go to my propane furnace. And people are just fine. Okay? And the number of hours in my climate are more, because it's designed at minus 40, but still, I'm getting, how do I say that? I'm getting a big benefit from using electric heat from 60 degrees down to 25 degrees. Still a benefit. Right? That's what we want to do. Let's not be stupid about it. let's use our heads here. Use some common sense. Again, fossil fuels are not evil. We just want to use less of them. We also want to use less electricity too. Okay? Jay?
I think if we look at this practically, we have a society that has been using air conditioners to cool, so we have a summer peak. The way you're suggesting is if we use heat pumps just down to that same efficiency on the other side, we can match the summer peak in the winter
Yes.
and then switch to our alternative source. And
There you
then
go.
we shouldn't have a problem as we grow.
I agree, absolutely, yeah. You got it, and that, we just looked
That's
at
what you're
that.
saying.
That's what I'm saying, okay? This one here, the one we were just looking at, okay? So what we've done here, this is the heating demand, it's the same as the cooling demand, right? But we reduced our natural gas consumption by 95%.
Bingo.
What's wrong with that? We're not impacting the grid, we're still using electric heat, right? And for those hours that we don't want to go straight electric, just continue with your fossil backup. It's fine.
And isn't that what happened in Texas last year when they had that cold snap? They just had too many electric heaters coming on at 1.0 COP instead of
Yes.
heat pumps at 3.0 or 2.5.
Correct. Yeah, Well, they also had another problem. The windmills they were using weren't set up for cold weather. The oils in them basically congealed, and so they wouldn't turn over, and they didn't have electric heaters, like a crankcase heater.
Right.
They didn't have electric heaters inside them to keep the oil lubricated, and so they weren't turning over. That's what really happened. They didn't have cold climate windmills
Interesting.
like we do up north. Our windmill, yes, sir.
You mentioned that the heat pump use the ground source heat pump use half of the electricity that a regular air source heat pump takes.
Yes.
I would think that that would be not completely accurate, that the air source uses way more. Because when I took some training with our power company, they were like, the air source heat pump, I think the price was like $1.29 compared to like 39 cents for the, or 29 cents for natural gas and 39 cents for oil. So the air source heat pump is way more. And then you also said, I'm up north in New York as well, and you said that after 20 degrees, the air source heat pump doesn't work as well? Is that what you're saying?
It works, it just doesn't give you enough heat. If you look at these two lines here, let me see if I can walk over here, okay? So, this is the heat loss. This is the production of the heat pump, and so they cross at that point as the balance point. So below there, you're not getting enough heat from the air source heat pump to heat the building. All right? So you have to have some kind of backup heat source. It's going to continue to run.
Yeah, so you're going to have your bill is going to spike and you're still not going to get enough heat.
You could think of it that way, yeah. You should. Yes, you're using more electricity, and I'm still gold. So what I do, I just flat turn the thing off at that balance point, and go to my backup source, which happens to be a propane furnace. Okay? Now, interestingly enough, in Europe, what these guys do, the boiler manufacturers are now providing air source heat pumps. So you have a fossil boiler and you have an air-to-air heat pump. And what they do is they figure out what the cost is based on the heat pump's COP for the energy, and they look at what the heating cost is for the fossil fuel, and that's when they switch it over. So that you always get the most efficient, lowest cost source of heat.
What was that? I didn't hear you back here.
Pardon?
What was that you said in Europe?
In Europe, that's what they're doing in Europe.
What are they doing?
They're switching it over not based on an arbitrary outside air temperature for production of heat. They're doing it based on what's the lowest cost source of energy. How's that? Okay? That's what the Europeans are doing. Because their energy is very high cost. I mean, you're looking at costs in Europe of, again, electricity in Germany is 30 cents a kilowatt hour. We're 10 cents here. So 3 times. So they're trying to be very efficient, they're trying to come up with the lowest cost that they possibly can. In Germany, when they get done with all this, it's going to be 60 cents a kilowatt hour. It's going to be even more. Right? And you can see that right here, this graph. Each one of those blue points there is a country in Europe based on how much electricity they generate from renewables. So,
One other question, how do you keep your bill down if you're using the air source heat pump? You have solar?
yeah. How do you keep your heat down if you got an air source heat pump? You can't. As it gets colder, it's less efficient, it produces fewer BTUs, and you got to run it longer or make it bigger. So you can't. That's the problem.
It's the worst choice.
Yeah, it's as Ralph says, it's the worst choice. Yeah, right. If you're going to use a heat pump, it's at the bottom of the heat. Okay, air to water is next, and water to water is the top. If you want to talk about that. In terms of cost, operating costs, the air to air is the highest, followed by air to water, followed by water to water geothermal. Right. Well, maybe that's all going to change with new technology. We don't know, but that's, first and second law of thermo will pretty much dictate how all this stuff is going to happen. Can't get around physics, unfortunately. Yeah. Does that answer your question?
Yeah, I'm a certified geothermal installer, so I'm
Okay.
trying to do.
So, I'm singing your tune, and I didn't even know that. Oh, she's not even a plant, see? Yeah, right. To answer your question, an air-to-air unit just, what, you get down to those kinds of temperatures, it just gets more expensive, less comfortable. Yeah,
Do you have time to talk about something hypothetical?
yeah sure.
What if we were able to change the source of our heat to multi-source our heat? Not just from the air, not just from the ground.
Yeah.
Not just go to the heat rather than be stuck in one heat.
Right, so what Ralph is talking about, we're talking about air to air, air to water, and water to water, right? What if you put them all in one box and then pick the best one for whatever was going on?
Or whatever the temperature is.
Isn't that cool?
Yeah.
Well, he has one. This is Ralph Ferry with Multi-Aqua. He's the only guy in the industry that has it. It's pretty cool.
Well, I didn't want you to say that, but
Because what you can do with it, Ralph, that water-to-water guy, instead of the ground, you can use solar.
absolutely.
Right?
And all day long, you can use photothermal and charge the ground, or charge a tank, whatever
You
you
could
want.
do that.
All that out long.
That's great.
Thermal energy storage.
Yes, thermal energy storage. So there are people working in the industry on trying to make this whole electrification the best that we can at this point. We just need to be, we just need to use some common sense. It's okay to talk about electrification, but not if it doesn't make any sense. Okay? There's a limit, that's all I'm saying. Okay? And we're just trying to help you, show you what the opportunities are, and then that best tool can help you then evaluate different systems and what's going to be the best choice for your customer. Okay, any other great questions? All right, folks, well, thank you very much. We really appreciate your time.